You know what drives me absolutely crazy? Everyone, and I mean everyone, thinks they understand how energy moves. They'll tell you with complete confidence, oh yeah, electrons flow through wires like water, through pipes, carrying energy from the power plant to your light bulb. Wrong. Dead wrong. And the really maddening part? This isn't some obscure quantum mystery. This is basic electromagnetics. But somehow, we've managed to teach it so badly that even electrical engineers, people who design circuits for a living, have it backwards. Here's what'll blow your mind. When you flip a light switch, the energy that lights your bulb doesn't actually travel through the wires. The electrons in the wire barely move at all, maybe a few millimeters per hour, like molasses going uphill in January. Yet your light turns on instantly. So where does the energy actually go? How does it get there so fast? The answer is going to sound insane, but I'll prove it to you. The energy travels through the empty space around the wire, through the air, through the vacuum. The wires are just there to guide it, like guardrails on a highway. Don't believe me? Good. You shouldn't believe anything until you see the evidence. Let me start with a simple question that'll expose the whole mess. You've got a battery, 2 long wires, and a light bulb. The battery is here, the bulb is way over there, let's say 1 light second away. That's about 300,000 kilometers, roughly the distance from Earth to the moon. You connect everything up, close the switch, and start your stopwatch. How long until the bulb lights up? Now, most people, even smart people, will say, well, electrons have to flow from the battery through the wire to the bulb, and they move pretty slowly, so maybe hours, days. Others, who've heard that electricity moves at the speed of light, will say 1 second, the time it takes light to travel that distance. Both answers seem reasonable. Both are completely wrong. The bulb lights up in about 1 meter divided by the speed of light. That's roughly 3 nanoseconds. Even though the battery and bulb are separated by 300,000 kilometers of wire, the bulb knows about it in the time it takes light to cross your kitchen. How is that possible? Because the energy doesn't travel through the wire at all. Look, here's what's really happening, and this is where it gets beautiful. When you close that switch, you create an electric field that starts propagating outward from the battery at the speed of light. This field doesn't say, hold on, let me check where the wires go. It just spreads out through space in all directions. Now, the battery also creates a magnetic field because current is flowing. And here's the key to understanding everything. There's something called the Poynting vector, and it's defined as E times B, the electric field crossed with the magnetic field. This vector tells you the direction and magnitude of energy flow. And where is this Poynting vector? It's in the space around the wires, not in the copper, in the electromagnetic field that fills the space. When those fields, electric and magnetic, reach the light bulb, traveling through space at light speed, taking the direct path, not following the wire, they induce a current in the bulb's filament. The bulb lights up. 3 nanoseconds. Done. The electrons in the wire, they're not the messengers. They're more like, to imagine a long tube completely filled with ball bearings. You push on one end, and the one at the other end moves almost immediately, even though the individual bearings barely shifted. But even that analogy is too generous, because the electrons hardly matter for the energy transfer at all. I can see you're skeptical. You're thinking, come on, Feynman, this is nonsense. If energy travels through empty space, why do we even need wires? Excellent question. The wires are there to guide the electromagnetic field. Think of them like this. When you have a current flowing through a wire, you create a very specific pattern of electric and magnetic fields around that wire. Those fields are strongest right near the wire surface and fall off as you move away. The configuration of the wires, their geometry, their spacing shapes these fields and directs the energy flow. A transmission line, like a coaxial cable, is really just a carefully designed structure to guide electromagnetic energy through space. The center conductor and the outer shield create a particular field pattern, and the energy flows in the dielectric, the insulator, between them. We fill that space with plastic or air specifically to carry the energy. The metal is just the scaffolding. You want proof? Here's an experiment anyone can understand. Take a circuit with AC current flowing alternating current. Measure the magnetic field around the wire. Now calculate the Poynting vector from the electric and magnetic fields. Integrate it over a surface surrounding the wire. You'll find that the total energy flowing through that surface through empty space exactly equals the power being consumed by your load, down to the last watt. The math doesn't lie. But here's where it gets even stranger. Remember those electrons I mentioned, barely moving? In a typical copper wire carrying household current, the drift velocity, the actual speed of electron motion, is about 1 millimeter per hour. Per hour! A snail could outrun them while taking a nap. Yet you flip a switch and your computer turns on instantly. You send a signal down a cable and it arrives at nearly light speed. How? Because the signal, the energy, the information isn't carried by the electron motion. It's carried by the electromagnetic wave propagating through the field around the wire. The electrons are just there to maintain the field pattern. They slosh back and forth in AC circuits, barely moving in DC circuits, but their motion isn't the message. They're like the guy standing next to the radio tower waving his arms. He's not the radio wave. He's just part of the equipment that makes it. This is why physics is so much fun and so much frustrating work. The universe doesn't care about our intuitions. It doesn't care that thinking about energy flowing through wires makes more sense to our monkey brain. Nature does what it does. And our job is to shut up and calculate, then accept what the math tells us. The wire is a waveguide. The current creates the fields. The fields carry the energy through space. The electrons barely participate in the energy transfer at all. And once you see this, really see it, you'll never look at an electrical cord the same way again. That innocent-looking cable isn't a pipe for electricity. It's a sophisticated device for shaping and directing electromagnetic fields through the space around it. The energy is in the emptiness, always has been. Now, if you've stuck with me this far, you're probably thinking, okay, Feynman, fine. Energy travels in the field around the wires. But come on, this is just a technical detail, right? Who cares whether it's in the copper or in the air next to the copper? Wrong again! This isn't a detail. This changes everything about how you should think about electricity, circuits, and energy itself. And I'm going to show you why this matters in ways that'll make your head spin. Let's talk about a battery powering a light bulb with a simple circuit. Standard stuff. You've got current flowing, the bulb is glowing, everything's happy. Now, where is the energy being dissipated? In the bulb, you say. The filament heats up and glows, right? But how does energy get from the battery to the bulb? You've already learned it's not traveling through the wire. So trace the Poynting vector, trace the actual energy flow. The electric field points along the wire from high potential to low potential. The magnetic field circles around the wire because current creates circular magnetic fields. Cross those two vectors. And you know what you get? The Poynting vector points radially inward from the space around the wire into the resistor or bulb. The energy is flowing through space, then diving into the load where it gets dissipated. The electromagnetic field in the space around your circuit is literally feeding energy into the components. It's like the circuit is sitting in an invisible ocean of energy, and the components are fishing it out of the water. The wires aren't pipes, they're fishing rods. Here's another one that'll cook your noodle. You've got a charged capacitor. Where's the energy stored? Between the plates, most people say, in the electric field. Correct. The energy is in the field, not in any material. It's stored in the stress of space itself, in the electromagnetic field that exists in the gap. You can calculate it. Energy density equals epsilon 0 E squared divided by 2. It's sitting there in empty space, or in the dielectric, which is mostly empty space, at the atomic level anyway. Now discharge that capacitor through a resistor. Watch the energy density in the field decrease. Watch the pointing vector carry that energy from the field between the plates, through the space around the wires, into the resistor where it becomes heat. The energy never touched anything solid during its journey. It went from field through field into agitated atoms. But here's where it gets really crazy, and this is the part that made me lose sleep when I first understood it. The field is all there is. Listen carefully. When we talk about electric current causing a magnetic field, we're thinking backwards. The current doesn't cause the field. The field is the primary thing. The motion of charges is just our way of describing changes in the electromagnetic field. The field isn't some ghostly side effect of real particles pushing around. The field is the reality. The particles are just excitations, little knots of concentrated energy in that field. Think about it this way. An electron isn't a tiny ball with a field around it. An electron is a particular configuration of the electromagnetic field and other fields. But let's stay classical for now. When you push electrons through a wire, you're really creating a traveling disturbance in the field. The field adjusts itself, and that adjustment propagates at the speed of light, carrying energy through space. You want something really wild? Consider two parallel wires carrying current in the same direction. They attract each other. Why? The standard answer is magnetic force between currents. Fine. But look at the energy in the electromagnetic field between those wires. When they move closer together, the total field energy decreases. The system is rolling downhill in field energy space, and that energy difference becomes kinetic energy of the wires moving together. The wires aren't pulling on each other through some spooky action at a distance. The electromagnetic field has an energy density at every point in space, and the configuration of lowest energy is when the wires are closer. The field pushes them together by being less stressed when they're near each other. Everything is local. Everything is field. Now here's why this matters for practical stuff, not just philosophy. When engineers design high-speed circuits, computers, phones, anything operating at high frequencies, they have to think about the fields. At high frequencies, the wavelength of the electromagnetic signals becomes comparable to the size of the circuit. You can't pretend energy travels through wires anymore because the circuit is smaller than the wavelength. At those speeds, a wire is an antenna. It radiates energy into space. Signals reflect off impedance mismatches. The circuit board itself becomes part of the waveguide structure. Engineers have to solve Maxwell's equations, the field equations, to predict what the circuit will do. The simple current flows through wires model doesn't just break down, it gives completely wrong answers. And this is the beautiful, frustrating thing about physics. Nature doesn't care about our convenient lies. At low frequencies, you can pretend current flows through wires and energy is carried by electrons, and you'll get close enough to the right answer that your lamp turns on. But push the frequency up, make things smaller and faster, and suddenly reality smacks you in the face. The fields were always there, always doing the work, you just weren't looking at them. So when you go home tonight and turn on a light, I want you to imagine what's really happening. You close a switch. An electromagnetic wave erupts from the switch at the speed of light, propagating through the air around your wiring. It reaches the bulb in nanoseconds. The fields electric and magnetic, dancing together, induce currents in the filament. The electrons jiggle. They crash into atoms. Energy converts from organized electromagnetic field into random thermal motion. Light emerges. And through it all, the energy never touched the wire. It flew through empty space, guided by copper, controlled by geometry, obeying Maxwell's beautiful equations. The emptiness isn't empty. It's full of fields, full of energy, full of reality. That's how energy really moves. And yeah, it's weirder than you thought.